So Zhanzhao from Penn State is going to talk about data-driven concrete science, applications, challenges, and best practices. Thank you.
Well, thank you so much for the introduction. So my name is Zhanzhao Li, and hello everyone. It's my great pleasure to welcome you to this presentation. I'm from Penn State. I'm a PhD candidate supervised by Dr. Alexandra Woniska. And this presentation is based on our recent publication related to the application, challenges, and best practices about data-driven concrete science. As you may all know, concrete is the most widely used man-made materials in the world, and it has been used in nearly any type of infrastructure elements, including buildings, bridges, roads, and dams, and so on. However, concrete is very complicated. It's made out of various components like cement, water, aggregates, and mixtures, which yields multiple phases like solid, liquid, and gas phases. So there have been a lot of research efforts in understanding these materials and trying to better design concrete materials for industry use. So taking an example of concrete mixture design, essentially we want to vary the composition of concrete, and as such we can achieve a certain amount of property, such as fresh properties, hardened properties, or durability, and so on. However, this would come with some challenges. First of all, there could be virtually infinite combination of constituents that could allow us to achieve the same property as this here. So the proposed mixture from experiments might not be the most cost-effective one or the most environmentally friendly ones. And secondly, the chemical and physical properties of the raw materials might have wide variability, and as such, this wide variability would have a very significant influence on the concrete properties. So by using the traditional approaches to design concrete or link the composition of concrete to the property might be challenging. So can we better understand these materials and towards a better design of concrete materials? And the answer is yes, we can use data-driven models. So by using data-driven models, we can utilize the experimental data as well as the computational data accumulated over the past few decades to better understand these materials and to design these materials. And this could lead to the paradigm shift from empirical science, theoretical science, computational science towards data-driven science. So the first part of this presentation will be related to the application of data science in concrete materials. So we first conducted a literature review of 389 publications, and we find that the number of publications increased gradually from 1990, and then exponentially since the past decades. So it shows the greater interest of the use of data-driven models from the concrete communities. So how does concrete science benefit from data-driven models? First of all, data-driven models can accelerate concrete mixture design by providing rapid property prediction. So an representative example is compressive strength prediction, where you can link the type and quantity of concrete constituents to compressive strength. And this can be followed by the optimization procedures to identify mixtures that has the lowest cost and the lowest environmental impact. So this would enable us to have a solution towards screening concrete mixture proportions that can be tailored to meet design specifications while reducing time and labor intensity for experiments. Secondly, data-driven models can also advance materials characterization and data interpretation. So current characterization techniques with increased spatial and temporal resolutions have produced a large amount of experimental data that pose a lot of challenges in terms of data curation and data interpretation. So with the use of data-driven models, we essentially can automate this process of curation and interpretations by achieving a human-level accuracy and beyond. So take an example of X-ray CT images. We can utilize deep learning to automate the segmentation process of the faces like pores, fiber, sand, and cement matrix. And as such, we can facilitate the quantification of the faces or microstructure in terms of the content, size, and orientations, which help us to better reconstruct the microstructure for numerical analysis. Thirdly, data-driven models can also enable accurate simulations of increasingly compressed cementitious system. So as you may know, molecular simulations techniques will also come with a lot of challenges, like it requires large amount of computational costs, and the simulation system is limited by time scale and a small amount of atoms involved. But with the use of data-driven models, we can essentially accelerate the development of interatomic potential, and as such, it can allow us to simulate a system with a larger amount of atoms and in a longer time scale without compromising the quantum chemical accuracy. So the first takeaway of this presentation is that data-driven models can allow us to accelerate property prediction, materials characterization, and material simulations. So the second part of this presentation would be related to challenges associated with the use of data science in concrete research. So first of all would be about the data challenge. So as indicated by the name, data-driven models are driven by data. So the quality of data is very important in terms of the performance of the models. However, the data quality in concrete science might not be very sufficient. So as one of the outcome of our literature surveys, we find that most of the studies related to the use of data-driven models in concrete research has a very limited amount of sample size. And essentially, over 50% of these studies has a sample size of less than 200 data points. And only 11%, about 11% of these studies would have a sample size over 1,000 data points. So this could be due to the fact that data collection process is very costly and time-consuming. Essentially, we need to cast multiple samples, cure them for 28 days or maybe up to years for durability studies. And even though we have hundreds of thousands of concrete mixtures and their corresponding properties available in the literature, it's difficult to collect them and organize them in an efficient manner because there could be different data reporting formats and with inconsistent level of completeness of the information in the literature. And second of all, validation challenge. So validation is very important to ensure the model generalizability. However, the use of validation methods might not be systematically used in concrete literature. So for example, there are two-way whole methods and cross validation on the whole data set, which can be used for model evaluation purpose without any special hyperparameter tuning. So, however, it cannot be used for model selection because it only involves the use of training and testing set. On the other hand, there are other methods like three-way whole methods like this, and cross validation on the whole training set. This can be used for both model selection and model evaluation. And the reason for that is that it involves the use of validation set such that you can do some special hyperparameter tuning or do your model selection. However, for the two-way whole methods, researchers might be tempted to reuse the testing set here tune your parameter and to select your model. So this would lead to data leakage and as such some misleading conclusions or overestimated of your generalizability of the model. And both two-way and three-way Hall methods only involve a single split of the data, and this would be less robust when you have a very small data set, which is typical case for concrete research. And moreover, the term cost validation might be loosely used in the literature. So for example, we will know that model selection and hyperparameter tuning is typically reported in the literature. However, is it often unclear if the cost validation is performed on the whole data set or on the training data set. So for the first case, it will lead to the inferred estimation of the generalizability, and as such, there could be some misleading conclusion out of this validation method. So after we deal with data and validation, we need to figure out how to interpret the model. So in this presentation, we are going to talk about interpretability challenge, focusing on the sensitivity analysis using permutation feature importance. So let's say we have a data set with a bunch of input and output, and then we feed them into a model, and then we get the predicted output and associate with the accuracy. And if we are interested in the importance of the variable water or the sensitivity of the model with respect to the input water, we might randomly shuffle all the values inside this input variable water while keeping all the other variables unchanged. And we feed this new data set to the model and get another accuracy, which is after the permutation. And we can repeat this process several times to calculate the average differences between the accuracy before and after permutation. And as such, we would get the feature importance of the input variable water. But when we look into this figure showing the relationship of superpositizer and water, we might find some issue here. So for the red circle, which represents for the real data set, it shows kind of the inverse relationship between the superpositizer and water. And this makes sense because one of the objectives of using superpositizer is to reduce water. And then the red plus would represent for the generalized mixtures after permutation. Essentially, I randomly shuffle the values of water variable while keeping the variable superpositizer unchanged. And you may find these two interesting regions. For example, for the region located on the top right-hand side, it has the highest amount of water and highest amount of superpositizer, which will lead to segregation process issue and the excessive breeding issue. And for the region, for the mixtures located in the bottom left region, it has the lowest amount of water with zero content of superpositizer. So this will lead to the fact that the mixture might have sticky property and it might fail to meet the workability requirement. So such unconditional permutation would generate the unrealistic concrete mixtures like these two regions. And this mixture would just force the model to detect the regions that might have limited to no data during the training or in reality, and as such, it might lead to misleading conclusion. So the second takeaway from this presentation is about the challenges, and challenges is still exists in terms of the data, validation, and interpretability. So last but not least, best practices. So we will recommend to share sharing of data and tools. So very few large data sets are publicly available right now. So there is a need to develop new data repository and broaden its accessibility. And secondly, there's also a need to develop guidelines or standards for reporting and sharing data such that the future researchers can collect those data with minimum efforts. Yeah. And we also encourage to share the computational details such as the model details, training procedures, as well as the source codes so that we can lower the barrier to model reproducibility and external validation. We also recommend to develop techniques to adjust the data scarcity, such as using transfer learning or knowledge-guided machine learning. And for wider adoption of machine learning or data-driven models in the construction or concrete industry, there is a need to understand or link the laboratory data to field data. So can a model developed on laboratory data predict for the field data? This is something we need to answer in the near future. Last but not least, knowing when to trust the model. So before trusting and deploying a model, we may need to ask the following few questions. Is a model with 90% accuracy more trustworthy compared to that with 70%? Are there any improper implementations mentioned previously? And can the reported accuracy of a model precisely reflect the performance on real-world data? So with that in mind, I would like to conclude that the field of data-driven concrete science has recently experienced a surge of interest. Data-driven models should be implemented with extra cautions, and we also propose some best practices for the better use of data-driven techniques in the field of concrete science. So with that, thank you so much. I will be very happy to answer any question that you might have.
Yes, thank you. My name is Emilio Garcia. I'm a professor in University of Leeds. I just wanted to add a couple of comments, really. When you mentioned the quality of data, the points you made are very valid, but they are not necessarily concerned with the quality of data, but the size of the data sets that are used in the different studies. The comment that I wanted to make in relation to specifically quality of data is, for example, that there's many instances of incomplete information reported in papers, for instance. In a recent analysis of over 20 years of papers that I did, almost half of them didn't report the cement type and strength class of the cement, for instance, or they didn't specify if the water content in the mixes was the effective or the total water. The second point that you very interestingly made were about the correlation between superplasticizer and water amounts. That is certainly a good point, and I would encourage everyone to keep that in mind. That problem. I mean, concrete science is multicollinear. Every one variable is depending on the other variables in the mix, and we seem to forget that. And the last comment I think that you made in a couple of slides ago, I think it was very important about how can we trust the model. I mean, if with an accuracy of 90%, a model is better than a model with an accuracy of 70%. There is something called the accuracy paradox, which means that the more accurate, I mean, if you get a model with a 95, 96% accuracy, probably it is less robust than a model which has a lower accuracy, but allows more flexibility in order to fit new data. So sometimes we are obsessed about the accuracy of our models and we forget about cross-validation and all these aspects that you have mentioned. So I just wanted to comment on those 3 points. That's it. Not really a question, sorry.
Thank you. You make a lot of great comments.
Yes, thank you.
Thank you.
Hi, I'm Ana Gamos for Argo Cement. And I guess some of the elements you put in this presentation are really interesting. What happened with ready-mix business is we have a lot of data about batching, a lot of stuff, but the data related with the testing part, it's something that could be a nightmare because it's not your data. It's data for other people that brings to you. My question to you is, what is a good number in terms of data? I know it depends on each scenario, right? But when you could bring all your batching information and your data information from the field put together and try to combine and predict some of the parameters that you want, but probably mainly compressive strength, what is considered a good number, a good data? And try to go beyond that scarcity of data.
Yeah, thank you so much for a great question. Unfortunately, I have to answer like it depends. Like it depends on the model capacity and the nature of your data and the goal for your applications. But in general, there are also studies showing like when you increase the amount of data, the model would become more stable. So I would say maybe it's good to start from 1,000 for research purpose. And if you have a lot of resources, 10,000 would be also a great number to start from.
Okay,
Thank
thanks.
you.